Welcome. This slideshow is going to, or this video is going to cover the material that we should have covered, but didn't because we had to do the paleomagnetism activity. So we're going to pick it up with where we left off at the end of the last lecture, before test number 1, where we were talking about weathering. And I will point out that we had just introduced a potential essay question. The potential essay question being, what are the two main forms of weathering, and what does each do to rocks? The two main forms of weathering which we began to discuss were mechanical and chemical weathering. And we were just to the point of having to get into those in more detail, which is where we will pick it up. We will then go from there on into talking about chemical weathering, and we will talk a little bit about soils, and that'll finish this chapter, and then we will move on into the next chapter. So, let us get started. With mechanical weathering. Mechanical weathering is the process by which rocks are broken into smaller and smaller fragments without necessarily changing the composition. This is basically what you tell me for the essay with respect to mechanical weathering. Mechanical weathering breaks rocks into smaller pieces or smaller fragments. This process does not change. Now, you don't need to include this in the essay, but mechanical weathering doesn't change the chemical composition of the rocks. It only changes the size of the fragments. And mechanical weathering can be accomplished through a number of different processes. We're going to look at 3 different processes here, but there are other processes that can also work to break rocks apart. The first of the processes we're going to consider is frost wedging. Frost wedging occurs when you have water that seeps into cracks and then freezes. As water freezes, it expands. Ice is less dense than liquid water is. So, as water freezes and expands, it forces the cracks further open. When the rock thaws out again and the ice melts, that means there's more room for more water to seep into the crack, and when that additional water freezes, it forces the cracks even further open. So, you get this freeze-thaw cycle that causes the frost to force the cracks further and further open, breaking the rocks apart. So let's consider some locations and determine whether these would be places where frost wedging would be important. For example, would frost wedging be important here in Laredo? Now, all of you should be saying no to that question. Why? Because it rarely gets below freezing here. We do get below freezing temperatures sometimes in the winter, but not that often. So that side of the cycle doesn't work here in Laredo. Let's consider another location. Would frost wedging be important in Antarctica? Now, if you're like most people, most of my classes, you're going to say, yeah, frost wedging would be important there. But would it? Remember, you've got to have this freeze-thaw cycle. And Antarctica is not thawing out. So Antarctica doesn't get the thaw side of the cycle. So frost wedging wouldn't be so important in Antarctica either. The place where frost wedging is important is where you get a daily freeze-thaw cycle. This usually occurs in mountainous regions, in more temperate climates, particularly in the spring and fall, where you can have this daily change in temperature that goes from above to below freezing. Another process is unloading. Unloading occurs with large plutons. These usually form fairly deep in the earth. And then, as the overriding rock layers are removed by erosion, the weight on the pluton and therefore the pressure on the pluton decreases, and the pluton begins to expand. The outer layers tend to expand more rapidly than the inner layers, which causes the pluton to fracture, usually in these onion-like layers that can then spall off. This is a process known as sheeting, and the result is a structure which we call an exfoliation dome. And what we're seeing here in this picture is Half Dome in Yosemite Valley, California, which is an exfoliation dome. Now, to get an idea of the actual size of this structure, ignore the Yahoo here in the foreground. What you want to pay attention to is this person, these people, those people, that person there. Those are people climbing up the side of Half Dome. They give you the better idea as to just how big that structure is. The next process we will consider is biological activity. Both plants and animals can break rock apart. In the case of plants, we've got a beautiful example here. This tree put roots down into the cracks within the rock. And then as the roots grew wider, it forced those cracks further open, thus breaking the rock apart. Now, as I said, both plants and animals can break rocks apart. Which organism do you think is best at mechanical weathering? And at this point, I usually let the students make a few guesses. And then, when they don't get the right organism, I tell them to look at their neighbor. Yes, we humans are probably best at mechanical weathering. This is a result of human-caused mechanical weathering. This is the Bingham Canyon Copper Mine in northern Utah. This is the world's deepest man-made pit. To give you an idea as to just how big this pit is, we're going to focus in on the area in the rectangle. We focus in there, and this is a dump truck. That's a dump truck. That's a dump truck. That's about how big those dump trucks are. Yeah, these dump trucks are so big, they have to be carried to the site in pieces and assembled on site. So now you can get a better idea as to just how big this pit is. So we zoom back out. There's another dump truck. There's another one there. It's a very impressive pit to stand on the rim of and look down into. It's even more impressive to be down on the bottom looking up. I've done both. I've got some samples in my office that came from this pit. So, these are some of the processes of mechanical weathering. Next, we have chemical weathering, the other form of weathering. Chemical weathering is the process by which the chemical composition of the minerals are altered by surface processes. So, this is what you tell me about chemical weathering for the essay. Chemical weathering alters the composition of the rock. So mechanical weathering breaks the rocks into smaller pieces. Chemical weathering alters the composition of the rock. Now, I will point out here that while mechanical weathering does not in and of itself alter the composition, mechanical weathering does make chemical weathering more efficient. This is because as you break the rocks into smaller pieces, you increase the total surface area for the chemicals to react against. So, mechanical weathering helps chemical weathering. But once again, for the purposes of the essay, you basically tell me mechanical weathering breaks rocks into smaller pieces and chemical weathering alters the composition of the rocks. Now, there are a number of processes by which the chemical composition of the rock can be changed. One of the more important of these is water and carbonic acid. Water is the most important agent of chemical weathering. I believe I've pointed this out before, but it should amaze you how many places water is important. Water is often the most important agent in many processes. Water can dissolve oxygen and thus be a powerful oxidizer. This can affect especially iron minerals, helping to oxidize them, helping them to rust. Water can also dissolve carbon dioxide. When carbon dioxide dissolves in water, it creates carbonic acid. This is a fairly weak acid, but it can still be pretty effective in helping to decompose the rocks, to alter the composition. And that reminds me of something I should warn you about. It would be correct to also say, with respect to the essay question, it would be correct to say that mechanical weathering disintegrates rocks and chemical weathering decomposes rocks. But I've had students who throw those terms out in the essays in ways that make it clear they don't know what those terms mean. To disintegrate is to break into smaller pieces. To decompose is to alter the composition. But students might say something along the lines of one of these forms of weathering decomposes and disintegrates the rocks, which shows they don't know what they're talking about. So you may use those two terms, but you still have to explain what they do to the rocks. So, carbon dioxide. Now, carbonic acid can also be released into the water as a result of rotting vegetation, rotting organic material. This also releases carbon dioxide into the water, which helps to form carbonic acid. So, how do rocks weather? How do these things affect, say, a granite we'll consider. Now you should remember that granite consists mostly of quartz and feldspars, but it may also contain some ferromagnesium minerals, such as biotite and amphibole. Potassium feldspar reacts with the carbonic acid and water to produce clay minerals and calcium bicarbonate, which is water soluble, and some silica in solution of the water. Clay is the most abundant product of the weathering of feldspars. Not just potassium feldspar, but also the plagioclase feldspars. And as a result of this, some silica is released into solution as well in the water. Quartz is one of the most stable minerals there is. As I've mentioned before, quartz is one of the few major minerals that is potentially stable in all three of the major rock-forming environments. We find it as a stable mineral in igneous, sedimentary, and metamorphic rocks. So the result of the chemical weathering of a granite with respect to the quartz is just typically released into the environment as sand grains. The feldspars turn dull and then to clay, releasing the quartz, which tends to stay shiny. This table shows what happens to a number of minerals as a result of chemical weathering. Quartz, once again, tends to get released into the environment as sand grains, though some of it may dissolve and go into solution in the water. The feldspars form clay minerals with these various ions released into solution and some silica. Hornblende tends to form clay and iron minerals with these being released into solution in the water. Olivine chemically weathers to form iron minerals and these being released into the water as ions. Now, clay is one of the minerals that is stable at Earth's surface. So it accumulates in sedimentary rocks. The silica can eventually precipitate out on its own to form a rock we call chert. And some animals will extract the silica from the water to make shells. These are usually single-shelled animals that do that. The magnesium, sodium, calcium, and potassium may be used by living organisms to help maintain their biological activity, and the calcium primarily goes into making shells within certain animals that have exoskeletons. The iron typically combines with oxygen to form various iron oxides, which can give a yellowish to reddish to brownish stain to sedimentary rocks, depending on how much of the iron oxide there is. So, that is the results of chemical weathering. Which brings us to spheroidal weathering. As rocks are broken into pieces, the sharper edges and corners of the rock are more susceptible to chemical weathering than the flat surfaces are. This is because they have more surface area to volume. The result is spheroidal weathering, which we can see an example of here. Most of the time when we see rocks that are this well rounded, we expect them to have been transported some distance by liquid water, so they tumble. But in this case, chemical weathering removed the sharp edges and corners because those portions of the rocks were more susceptible to weathering than the flatter surfaces were. So, how fast do rocks weather? Excuse me. There are several factors that influence the rate of weathering, one of which we've already talked about a little bit, and that's the surface area to volume ratio. The smaller the fragments, the greater the surface area to volume ratio. And so the more surface area that is exposed to the chemical agents. So smaller fragments weather more quickly than larger fragments do. And this, as I've already mentioned, also affects more strongly corners and edges than it does the flat sides of the rock, because the corners and edges have higher surface area to volume ratios than the flat sides do. The second factor is the presence or absence of joints. That's the technical term for cracks in the rock. A joint is a crack along which there has been little motion. That's something we'll be talking about in more detail later. But joints provide conduits by which water can more easily penetrate into the rock. They're part of that increased surface area to volume ratio that we were just talking about. The final the next factor is the mineral makeup of the rock. Some minerals are more susceptible to weathering than other minerals are. Here we have a couple of examples. This is a granite tombstone from 1868 versus a marble tombstone from 1872. So this tombstone is younger, but this tombstone is much better preserved. That's because the minerals that make up the granite are much more resistant to chemical weathering than the minerals that make up the marble. Marble is made of the mineral calcite, and calcite is very susceptible to dissolution by acids, including carbonic acid, which we talked about before. Whereas the granite is not so susceptible. If you want a rock that's going to make for a tombstone that'll last the longest, though, the best is probably quartzite. Quartzite is a metamorphic rock made almost entirely of quartz. And as we've already talked about, quartz is one of the most stable minerals there is. The next factor is climate. Temperature and humidity both play a role in weathering. As we've talked about, alternating hot, warm, and cold, freeze and thaw helps to promote frost wedging. But there's more to it than that. The amount of water in the environment and the temperature also influence the rates of chemical weathering. Warm, humid conditions favor chemical weathering more strongly than cold, dry conditions would. And then this brings us to the process of differential weathering. As I've said, the composition of the rocks can influence the rate of weathering. Here we can see the results of differential weathering. Some of these layers in this rock unit were more susceptible to weathering than other layers. You can see how some of these layers have resisted the weathering versus other layers. Typically, this is especially true in desert environments. Typically, limestones and sandstones resist weathering. They tend to form cliffs in these types of environments, whereas shale tends to be less resistant to weathering. It'll tend to produce slopes. Differential weathering can also occur as a result in the difference in the way the specific minerals weather. And this can result in a rougher texture to some rocks as a result of the more susceptible minerals weathering, while the less susceptible minerals don't. Now, differential weathering, as I said, is most prominent in desert environments, in arid environments. It's less prominent, less noticeable in humid environments. And that brings us to soils. Soil serves as an interface between all four of Earth's spheres. As we'll see later on, in a few minutes, soil contains elements from the atmosphere, the hydrosphere, the biosphere, and the geosphere, the solid earth. So, what is soil? Soil consists of fragments of rock which taken together are called regolith. But regolith is not synonymous with soil. Soil is a mixture of regolith and humus and various amounts of air and water. You know what air and water are. But what is humus? Humus is organic matter from the rotting remains of animals and plants. This pie diagram shows a breakdown of the average composition of soil. Your average soil is about 45% regolith, 5% humus, and then varying amounts of air and water. Just how much of each of these components there is in a particular soil is dependent largely on the environment in which the soil is found and the parent rock from which it formed. So what are the controls on soil? Well, one of the most important controls is the parent material. Parent material refers to the source of the weathered mineral material. It's the rock that broke apart to provide the regolith. The nature of the parent material can influence the soils in two ways. One, it affects the rate of weathering and therefore soil formation. For one thing, granite versus limestone. Granite, as we've talked about, is fairly resistant to weathering. So granite's not going to produce soil all that quickly. Limestone, on the other hand, is very susceptible to chemical weathering, as we've discussed. Limestone, once again, like marble, is made of the mineral calcite, so it's very susceptible to chemical weathering. Another thing about the parent material that affects soil is, are we talking solid bedrock or unconsolidated sediments? Solid bedrock isn't going to weather as quickly as unconsolidated sediments, which are made up of fragments. The parent material can also affect the chemistry of the soil, and therefore its fertility. Again, the types of minerals that make up the parent material will directly influence the chemical composition of the soil. They provide some of the chemical elements that go into the soil. The next factor that controls soil formation is time. How long does the material have to sit? The length of time can have a very profound influence on the nature of the soil. The longer the soil is allowed to just sit, the more time the environmental factors have to influence the soil. If soil only has a short time to form, then it's going to take on characteristics that are more closely aligned with the parent material. On the other hand, if the soil has a long period of time to sit, then it's got time to evolve. And other factors can influence the character of the soil. There is no set time period for the formation of a particular type of soil, though. The next factor is climate. This is probably the most important factor when it comes to influencing the nature of the soil. The most important factors here with respect to climate are variations in precipitation and temperature. These will influence which is more prominent in the soil forming process. Is it going to be mechanical weathering that's more prominent, or chemical weathering that is more prominent? Remember, more water would mean more of an influence of the chemical. Less water, less influence for chemical weathering. The rate, these can also influence the rate and depth of weathering. The amount of precipitation can also influence which elements are leached out of the soil as it forms, and which elements are left behind. Climate also influences the types and amounts of vegetation and animal life, which contribute to the organic material in the soil, which contribute to the humus. Which brings us to plants and animals. The types and amounts of organisms strongly influence the soil. Plants and animals provide organic material, the humus. Some bog soils, some soils that form in bogs or swamps, tend to be mostly organic material, whereas most desert soils only contain a small amount of organic material. When organic material rots, it releases nutrients into the soil, and it also provides organic acids which help to chemically break down the parent material. Microorganisms, fungi, and bacteria can also help to break down the plant and animal material to produce the humus. Burrowing creatures such as worms, gophers, moles, rabbits, what have you, armadillos around here, can also help to stir up the soil mix it, helping to better mix the humus and the mineral matter. And their burrows provide passages by which water and air can penetrate the soil. Topography is important. Steep slopes inhibit soil formation because things don't like to sit on steep slopes. They tend to want to move downslope. That's going to be something that we're going to talk about in a lot more detail when we talk about mass wasting. So the gentler the slope, the more time the soil has to form. Steep slopes also prevent water from soaking in, and they accelerate erosion. So soils tend to be very thin to non-existent on steep slopes. On the other hand, gentle slopes allow water to accumulate, allow for, say, bogs or lakes to form, which can allow for thick accumulations of organic rich materials in the soil. The optimum situation for soil formation is flat to undulating surfaces. The undulating surfaces provide some drainage, so water doesn't pond on the surface, but still allows water to penetrate, to soak in. Also important is the slope's orientation. This can influence the amount of sunlight the slope gets. Say in this hemisphere, in the northern hemisphere, a south-facing slope is going to receive more direct sunlight than a north-facing slope will. And that'll help to warm the soil, help to promote the chemical reactions, and influence the types and amounts of plant and animals that live in the soil. Now, all these factors work together simultaneously to produce soil. So you've got to look at them all when you're trying to figure out what's going on with soil formation. And this brings us to the soil profile. If you dig a trench in the ground and examine the soil, you will find that it consists of layers. The layers are caused by water percolating through the soil. As the water percolates through the soil, it leaches components from some layers and then deposits them in other layers. These layers are known as horizons. And a cross-section showing these horizons is called the soil profile. This is a fairly typical soil profile. You'll notice that we got a number of different horizons here. And we've got some portions that are referred to as the topsoil, and then some portions referred to as the subsoil. The uppermost horizon is the O horizon. The O horizon consists of dead organic material and generally teems with living organisms, insects, fungi, worms, etc. Beneath or as part of the the O horizon is just this thin layer right up here. Then we have the O horizon here, which makes up the rest of the topsoil. Or excuse me, the A horizon, which makes up the rest of the topsoil. The A horizon consists primarily of matter with up to 30% humus and still experiences much biological activity. And as I was saying, the O and A horizons collectively make up the topsoil. Next, we have the E horizon. There's very little organic material in the E horizon. Water moving downward through this layer tends to wash finer particles out of this layer, producing what is called eluviation. Water also tends to remove the more soluble components through a process known as leaching from this layer. Beneath the E horizon is the B horizon. This horizon is called the subsoil. The material eluviated and leached from the upper layers of the soil tend to be deposited in the B horizon. Because of this layer is also often called the zone of accumulation. Horizons A through B are collectively known as the solum, or true soil. Almost all life and soil creating processes are contained within these layers. The next layer down is the C horizon. This consists of only partially altered parent material. In the other horizons, the material bears little resemblance to the parent material. In this horizon, the nature of the parent material is fairly obvious. And this layer has not made the transition from regolith to soil. And then beneath the C horizon is the unweathered parent material. Now, this is the profile for soil that forms in a more temperate climate. Other climates will tend to have one or more of these horizons missing. Now, I'm not going to discuss the different classifications of soil. Those have kind of changed over the years, and to be quite honest, soils bore me. Soils were more important to my father, who was a botanist by training. But we will move on and talk about ore deposits that are related to these processes. Weathering can concentrate desirable elements into economical concentrations. And it can do this in two ways. One of these is by water percolating down through the soil, removing undesirable components and leaving the more desirable ones concentrated in the upper levels. The other way by which water can help, by which weathering can concentrate desirable elements, is by water leaching out the desirable components and then redepositing them at lower levels. One example of the first of these is bauxite. Bauxite is the principal ore for aluminum. It forms primarily in tropical environments where the area gets a lot of rain. The rain tends to leach other elements out of the soil, leaving behind aluminum oxides, which form the bauxite. And then we can come along behind and dig up the soil here, dig up the bauxite from the soil, and then process that to get aluminum. Now, aluminum, as you should recall, is number 3 on our all-time most common elements list in the Earth's crust. But most of the places where we find aluminum, it's locked away in silica minerals. these processes of chemical alteration change it from aluminum silicates to aluminum oxides. And it's much easier to extract the aluminum from the oxide form than it is the silicate. Then there are other ore deposits that can form from the other process as water deposits desirable elements. These would include copper and silver deposits, can be concentrated in these ways. Usually you start with a low-grade ore that contains pyrite, an iron sulfide mineral. As the pyrite weathers, it releases sulfuric acid into the environment. And this sulfuric acid helps to leach the silver and copper from the rocks and then carries it into the groundwater. Then change the chemistry within the groundwater can cause these metals to be deposited and concentrated someplace else. And so this can take more diffuse deposits and then concentrate them into something that is economical to mine. And this finishes this chapter, which means it's time for your next chapter quiz, which will be due when you walk into class on Monday. And that then brings us to chapter 6, where we take a look at sedimentary rocks. By the time we get done with this chapter, you should be able to describe the differences between cobbles, pebbles, sand, silt, and clay, and explain the relationship between class size and the extent to which class can be transported by moving water or by wind. Describe the characteristics of the various types of clastic sedimentary rock, including the significance of differences in composition of sandstone. Explain the differences in the characteristics and depositional environments of various types of chemical sedimentary rocks. Differentiate between various sedimentary depositional environments in both terrestrial and marine environments, and explain how the formation of sedimentary basins can be related to plate tectonics. Apply your understanding of the features of sedimentary rocks, including grain characteristics, sedimentary structures, and fossils, to the interpretation of past depositional environments and climates. Explain the importance of and differences between groups, formations, and members. So, sedimentary rocks. Sediment is the raw material of sedimentary rocks. Sediment is transported from its source by wind, waves, streams, glaciers. A number of different media transport the sediments. But eventually, these sediments are deposited in a variety of environments where they are lithified. Lithification is the process by which loose sediments become solid sedimentary rock. Sedimentary rocks constitute 75% of the rock outcrops on continents. So as you look out at places where rocks are exposed, where the bedrock is exposed at the surface, 75% of those rocks that you're going to see will be sedimentary rocks. There are different types of sedimentary rocks that we will be looking at as we go through this. There are three main groups. We have detrital or clastic sedimentary rocks, chemical sedimentary rocks, and organic sedimentary rocks. And this brings us to a potential essay question. The potential essay question being, what are the two main types of sedimentary rocks and how do they differ from each other? Now, for the answer to this essay question, the two main types are detrital or clastic and chemical sedimentary rocks. And we'll be taking a look at these and see how they are different from each other. So, our two main groups of sedimentary rocks are clastic and, as I said, chemical rocks. Clastic rocks. Now, you got two terms here that are synonymous with each other. Detrital and clastic. These two terms mean the same thing. And some geologists will use one term while other geologists will use the other term. Many of the books I've encountered use detrital, but the geologists under whom I studied use the term clastic. And so clastic is the term I'm more likely to use. But clastic rocks are made up of clasts or pieces, solid pieces of pre-existing rocks that are created by weathering. That is what clastic rocks are. Detrital rocks are made of the detritus or pieces created when other rocks weather. Now, these pieces, and that's basically what you would tell me about these types of rocks for the essay question, is that detrital or clastic, whichever term you want to use, is made up of pieces of pre-existing rocks. Something to that effect. Now, there's a wide variety of materials that can compose the pieces that make up detrital rocks. Though clay and quartz are by far the most common that we find, the minerals that we find in classic rocks. This is because clays and quartz are the minerals that are stable at Earth's surface. The other minerals we might find in the classic rocks generally are not stable. Clays, as we've talked about before, form from the weathering of many minerals, many different minerals. Quartz is released into the environment by the weathering of rocks that contain quartz. We classify the classic rocks based on the size of the fragments, how well sorted the fragments are, and how well rounded the fragments are. This diagram here, this table here shows how we classify them based on the size of the fragments. When it comes to actually giving the rock a name, a classification, we base the classification on the largest fragment that is present in the rock. It doesn't matter if there's just one of those fragments. That's going to define what the rock is. Let's see here. The size tells us something about the environment in which, well, actually, I think I'll hold off on saying that for right now. The other characteristics that we look at are sorting and how well rounded the fragments are. If you have a poorly sorted sediment, you're going to have a bunch of different sized particles. The better sorted the sediment, the more consistent the particle size is. And usually we tend to see better sorting with smaller fragments than with larger fragments. The larger fragments provide room by which smaller fragments can get deposited in between them. Whereas when you get a better sorted sediment, it's usually going to consist of smaller fragments that don't allow for other fragments to exist between them. Then there's also how well rounded the fragments are. This tells us how, to a certain extent, how far the sediments have been transported. Most fragments will tend to start off fairly angular, with lots of sharp, jagged edges and corners. But as they are transported, especially by running water, these fragments can bang into each other. And they can knock off the sharp edges and corners because those are the weaker parts of the fragments. And so over time, as the fragments are transported, they'll become better rounded. Now, note, rounding doesn't necessarily mean spherical. See, this is a very well-rounded fragment that's not spherical. Rounding just refers to a lack of sharp edges and corners. Also, composition can be influenced by the distance over which the sediments are transported. You may start off with a mixture of many different minerals, like you could have quartz and feldspars and micas and amphiboles in the rock. But over time, the micas, the amphiboles, the feldspars, they'll tend to get beaten to pieces and chemically altered as they're transported. Quartz will tend not to get beaten to pieces as easily. And as we've already talked about, quartz doesn't alter chemically all that well. Those other minerals I just mentioned, they will tend to alter to clays, which once again are more stable in the surface environment. So let's look at some of the different classifications. The largest, if a rock contains fragments that are over 2 millimeters in size, then fragments in that size range are referred to as gravel. And if they're over 2 millimeters in size, we can usually tell how well rounded the fragments are. So we subdivide this classification based on we subdivide these rocks based on how well rounded the fragments are. If the fragments are well rounded, then we call the rock a conglomerate. And this is an example of a conglomerate. As you look at this rock, you can see how well rounded the fragments are. There are very few sharp edges and corners on these fragments. On the other hand, if the fragments are very angular, then we call the rock a breccia. A breccia, in this case, as you can see it, has very angular fragments. These fragments were probably not transported very far by running water. These fragments didn't tumble. These fragments may have been formed as a result of frost wedging on, say, a cliff, and then fell down to the base of the cliff and were deposited right there at the base of the cliff, where they then became lithified and became a solid rock, with smaller fragments filling in the space in between. If the size of the largest fragment is between 1/16 and 2 millimeters, then the sediment is called sand, and a rock that's composed mostly of, or whose largest fragment is sand, has a very strange name of sandstone. Sandstone tends to be, well, the sand fragments tend to be big enough to where you can see them, but not so big that you can actually see the shape very easily. A sandstone, you'll also notice, will have a gritty, sandy feel to it. There are different types of sandstones. These types of sandstones are classified based on which minerals are present in the sand, which minerals make up the sand grains, for example. An arcosic sandstone will have a fair amount of feldspar mixed in with the sand grains, mixed in with the quartz grains. On the other hand, a wacky, let's see if I remember right, it's spelled W-A-C-K-E, a wacky will have a fair amount of clays mixed in with the sand. Some stones will be nearly pure quartz sand. If the fragments are 1/16 to 1/56 of a millimeter, that's the largest fragment, that sediment is called silt, and a rock whose largest fragment is silt is called a siltstone. Now, by the time we've beaten the particles down to this size, most of the other minerals, the feldspars and what have you, have been beaten to pieces. So the silt itself, and chemically altered, so the silt itself is almost entirely quartz grains. And there's typically a significant amount of clay mixed in with the silt, though there doesn't have to be. By the time we get down to fragments that are under 1/256th of a millimeter, we're mostly talking about just clay particles. Clay tends to be platy. That is, it's large in 2 dimensions, thin in the third, like a plate. What we call a rock whose largest fragment is clay, that's made up almost entirely of clay, depends upon how these clay particles are oriented. If the clay particles have random orientations, we call it a claystone. If the clay particles are aligned with each other, if they run parallel to each other, then we call it a shale. Clays can also have, or these shales and claystones can range in color depending on what other minerals might be present. If there's iron oxides in them, they might be kind of reddish or yellow in color. If there's a fair amount of carbon, they may be black in color. If it's nearly pure clays, though, they'll typically be more white in color. A very light gray to white in color. So, these are the clastic rocks. Now we move on and discuss the chemical rocks. We further break down the chemical rocks according to their sources. inorganic versus biochemical, and their compositions. Note that some of these can originate through both inorganic and biological processes. And it should also be noted that since they crystallize from essentially a liquid state, evaporites can have textures that are very much like those of igneous rocks. That is, some of these chemical rocks can be made up of interlocking crystals. Now, the most common forms of chemical sedimentary rocks form primarily from calcium carbonate that is carried in solution in the water, primarily from the mineral calcite. These minerals can come out of solution to form rock in one of two basic ways. The water can become oversaturated in the chemicals, causing them to precipitate out on their own. In the case of, or this can happen in the case in caves to form a rock we call travertine, which is a calcium carbonate rock, which is a form of limestone. It's also happening around the Great Salt Lake in Utah. In that case, the minerals that are forming is halite, which is precipitating out of the water. Salt, as the name implies here. These minerals can also be taken out of the water through biochemical processes to produce seashells. The most common of these types of rocks is limestone. Limestone is made of calcium carbonate, made of the mineral calcite, and it can form as a result of purely biochemical processes or biological processes. Here we have one example of limestone that formed entirely from purely chemical processes. This is one of the stalagmites in Carlsbad Cavern. This one is huge, by the way. We'll talk a bit more about this later on when we talk about groundwater. The other way is through biological processes. Here we have an example of limestone being deposited through biological processes. Here we're looking at corals in a reef. The corals remove the calcium carbonate from the seawater and use it to make their shells. And as the corals grow one on top of each other, limestone is accumulated beneath. This is El Capitan, the tallest point or the highest point in Texas, in the Guadalupe Mountains up in northern Texas. This, what you're seeing here, is the limestone from an ancient reef system. Now, these were not created by coral. This limestone came from other animals. And here are some examples of other animals that precipitate out calcite. Another common chemical rock is dolostone. This is made of the mineral dolomite. Dolomite, if you were in the lab, I believe you were exposed to it in one of the labs, is a rock that's made up of the mineral dolostone is made of the mineral dolomite, which is a calcium magnesium carbonate. Most dolostone is entirely inorganic in nature. Animals do not create, biological organisms do not create dolomite. Although the exact origin of dolostone is not entirely clear. It appears that most dolostone is the result of the chemical alteration of limestone. But under rare circumstances, dolostone can precipitate out on its own. And this is where we're going to call it quits for this lecture. And we'll pick it up next time by taking a look at organic rocks. But before we close, let me just go over the potential essay question that we had here. What are the two main types of sedimentary rocks, and how do they differ from each other? The two main types are clastic or detrital rocks. Choose which one you want to call it. You don't have to call it by both names. And classic rocks are made up of the pieces of pre-existing rocks that were created by weathering. Or I should say, classic rocks are made up of the pieces of pre-existing rocks that are created by weathering. Something to that effect. Something that tells me it's the weathering of pre-existing rocks. That's the better way to put it. Classic rocks are made up of the pieces that are created by the weathering of pre-existing rocks. Chemical rocks are made up of the ions that are released into solution in the water that then precipitate out. Chemical rocks are made up of the ions that are released into solution by chemical weathering that then precipitate out of the water. Something to that effect. And so, as I said, we'll pick it up by taking a look at organic rocks, and we will also, in the next lecture, take a look at structures that form in sedimentary rocks. And then we will move on in and talk about metamorphic rocks. And we will probably cover all the metamorphic rocks in the next lecture as well. So you'll have a couple of these chapter quizzes that come due in fairly short order. So you might want to get a start on the sedimentary rock one. You don't have to finish it. Answer those questions that we've covered so far, but leave the others unanswered, and you can come back after we complete this chapter. So this is where I'm going to close this lecture, and I'm going to wish you all a good day.